Good morning. I am Shen. That's how my friends call me, or I make my friends call me. I'm a project scientist in West Coast Metabolomics Center at UC Davis in Oliver Finn's group. So this is the opportunity I'm thankful for, to present our teamwork. That's almost everyone's name on the author list, and to share with you what we have been doing in terms of when we are always hungry and eager for more novel technology to look for a better detection level and have a broader coverage for metabolomics. And especially in the realm of exposome compound. Because when it comes to exposome compound, there are some voluntary exposure like the food and drink we put in our system, the drugs that make us feel better, hopefully heal, and the cosmetics, sunscreen we put, and also some involuntary exposure, like the air pollution, like the PFAS or plasticizer in our food wrappers and drinking water. And that content of that have big biological interests, but the diversity in the chemistry sphere is super wide diversity in terms of chemical properties, in terms of the resolution, in terms of the concentration range coming from millimolar in the blood down to micro, nano, picomolar in the blood. So that's where having an extended dynamic range comes really handy. It is a solution can help us detect trace level, low abundant metabolites, meanwhile not compromising on the quantification of nor saturating on the high abundant metabolite. In this case, is a liver extract, and we have the choline that we synthesize in the liver. We can also have dietary intake. Meanwhile, usually mask in the neighbor mask signal 3,000-fold less, and we have some compound coming from eating vegetables and fruits or drinking gin tonic. It's a kind of tannin. In this case, we're lucky to have a solution to be able to detect it or characterize it. But what about it is 10,000 times lower? What if it's 100,000 times lower? Are we still be able to capture it? So that's why the extended dynamic range will give us the solution to detect both trace level and high abundant, hopefully in the same run. So we don't have to split injection, one doing enrichment and purification, the other one doing dilute and shoot. And it can certainly intuitively broaden our coverage of metabolome, other metabolites at the same time, specific focus benefiting the exposome compound. And after we can reliably detecting them, of course, will aid into the quantification accuracy. So that's why we were super excited when we heard the Excidium Pro has the capability to do extended dynamic range. And in our lab, Uri and I went to give a shot doing a pilot study to see how it's going to benefit the coverage. So in principle, how it works, as I understand, is instead of the full scan, we're going to split the full scan into individual injection windows, into two series of subscans. And for the AGC target, that usually dominate by a high dynamic peak. But for the ion mass, for the mass range that has lower ion count, we can actually allocate more injection time to make use of reaching the same AGC target. So meanwhile, the high abundant one wouldn't be oversaturated, still keep a comparable signal, and the low abundant get a better chance to be detected because of the higher injection time. And later, the subscans will be stitched back together, so the data we get is still a full scan and help us with other software analysis or thermal-compatible analysis. So here's what we got from our pilot study. Uri and I brought a liver extract that's single-phase extraction. We run a weak C18 from basically 100% water to 100% ACN with modifiers, because we want to capture both polar metabolites and those polyphenol alkaloids, food compound, drug, to a little bit more hydrophilic compound in the same way. And the data is analyzed in MS-style version 5.5 and matched with Megamona that's available and produced in our lab, and NIST 23 as well. To start with, this super easy to use. We can just transfer our method from our current Orbitrap system, and with additional option like how many window you want, how big do you want, how much is the overlap. That's pretty much it. So we kept everything else the same and play with different size of windows. To start with, we can also start with just equal window size. And with some prior knowledge, maybe we can also design it into a more variable window size so that we know for the region that has a lower ion count, we can design for that. But that's our starting point, splitting the mass range from 60 to 1,000, both positive and negative mode. And immediately after the injection, we see an increase of MS1 features immediately for both positive and negative mode. That's about a 70% increase for both of that. And on top of that, we did acquire X for EDR mode off, EDR off on. Just to point out, and the sequence was interjected, like errored out in the beginning, at the end for the negative mode. So that's why for the fair comparison, we have 5 rounds of acquire X in positive mode, or for negative mode, this is the data we have for 1 round of acquire X. But it still serve the purpose. When we look at the number of MS2 annotations, we get to see slight increase of that, which we think maybe is the 5 round of acquire X for top 3 DDA, and that's about top 15. Maybe all of the low abundant still didn't get much chance to end up in the top 15 abundant, or it could be what is detected was not so available, matching in the current available mass spectral libraries. So we further take it on to match with our in-house MZRT reference library. That is MS2 level, or some community will call it MS3 level annotation. So that's where we see if we count both MS2-based, MZRT-based annotation, we get to see the increase of number of annotation benefiting from the dynamic, extended dynamic range. Zoom into what we get. What is the extra gain when we put on the EDR mode on? There are 2 examples. All right, and the top one, actually, it is in the EIC signal to noise. It is EDR on, you get to see better signal to noise, and that end up having a better chance to trigger MS2, whereas when it's turning off the EDR, it doesn't get to trigger MS2. And the lower is the previous example we saw in the tannin. That is, even though you see the overall EIC intensity, the peak height is lower when we look into the EDR mode on, but the signal to noise is significantly higher. And that affects the peak picking, and that affects the matching. So the lower one, I'm supposing there are different ways to do it. This is how the raw data looks like, but if we have some smoothing, maybe it's in the marginal area, we can still make it into a peak, but it's for human to judge on that is that really a real signal? And when we look at the signal to noise in both chromatography peak and also the spectra, also we see the enhance of signal to noise in the spectra as well. So something we always keep in mind, or whoever curating the metabolomics data set will be noticing some portion of in-source fragments in the data set, and they are also seeing this in public or licensed libraries. So we see it in the NIST 2023 library. Some of the annotation you see is like, oh, I'm cautious about if my intact molecule matching to this, what is it? So that we get to be skeptical about, is it really an in-source fragment happens or a good annotation? But also as we're building a database level annotation platform, which is the LCBIM base, we also try to get the chance to map out doing the statistics, like saying how much percentage is the in-source fragment. And it's about like one quarter, and the majority still keep as the classic like dimer or different ADAC form. So we just need to keep an eye on it. When it's detecting ions, we also try to, how do we further enhance that? So when we do a test, we also test for in-source fragmentation. The first example is phenylalanine. And in our current setup, in our first 2 instruments, the QE and Explorers, we get to see usually like 1/3 end up to be this in-source fragment happen to both the deuterium labeled standard and endogenous compound. And when we transfer the same parameters into Excidian, we see the reduce of in-source fragment immediately. And in-source fragment, when we were ranking different parameters, is basically dominating by the RF voltage. And RF voltage, if you keep increase it, most of your signal, if you look at TAC or our signal, will be having a positive feedback. So you want to keep increasing it. But to a certain point, your fragile compound will start to cripple apart. So that's something to keep in mind. And for Excidium, for their modification of their ion funnel, we get to see if we lower the RF voltage, we still see a quite decent signal in the intact molecule, and then meanwhile reduce the in-source fragmentation for that. The other example is inosine. And it's quite drastic because if our current setting with RF voltage of 50 on the Explorer series will just bombard it completely. You see two annotations of hyposensine earlier and later, and the later one is actually the in-source fragment of inosine. And that's something will cause false discovery annotation as well. But just because we have the standard, we know it happens, and then you know the earlier one is hyposensine, the second one is in-source fragment. Again, when we move the parameters to Excidium, then you start to see the intact precursor. And as we reduce the RF voltage, you also see you get a better chance to detect the intact precursor of inosine. Our work, our flow is super high, and one thing we always think about is can we make use of microflow, sometimes even nanoflow, to enhance the signal. And one of the reasons we have in-source fragment is because the parameters, the voltage, the temperature, and the gas we have to put to evaporate all of the high flow is so much. So the ESI is not so soft anymore. So one thing we think, can we dive into lower flow so that we can enhance the signal and also better the in-source fragment. So that's why we did a trial, also investigate on the nuomics. We were keeping the same chromatography because we built a lot of library based on that. So we're simply keeping the same high flow, but doing a split 1 to 50, turning 800 microliter per minute flow into a 16 microliter per flow. And the chromatography behavior retention time will be the same, but majority, the 98% of the flow and the sample will be diverted away. Even with that, so we're injecting much less, and each nozzle is splitting into 8 nozzles. We still see higher intensity and improvement. And when we put nuomics, the uni-ESI source on our QE, the biogenic amines detection in negative mode benefit from that, but still we are seeing 18 out of 30 internal standard represented here. Some are even lower, but still there. But when we do the same modification to the Excidium, we see 29 out of 30 internal standard, which helps the negative mode ionization really well. For more sensitivity, squad is the go-to. So in the beginning, the first one is talking about just when we are analyzing, this is an investigation to look into oxidized PC in lipoprotein in blood. And the oxidized PC is about 1,000-fold less compared to a typical PC. So if we run it just as our screen and targeted assay, we see a lot of PC, TGs, fatty acid, but what are the chances we'll see the oxidized PC? So if you run it and run the dilution series, we see the detection level can go as low as 10 picogram on column. And if we turn it on into a squad analysis on the same instrument, the detection level goes down 10 times more. And that's comparable with a triple quad, MRM style. And when we analyze the squad analysis in Astro, and it goes even lower for 10 times more. So overall, the squad analysis on Astro is 100 times more sensitive if we're compared to just to MS1 orbit trap quantification. Not just the sensitivity, but also the coverage of MS2 give us 2 to 3 times more features compared to Explorer's Acquire X, several injections. and adding up more annotation identity search. And this is also a solution MassCube proposed and recently accepted by our postdoc, Dr. Huaxu Yu. If you want to know about this, this is more like fast one-click Python package. He will be talking about it tomorrow afternoon. And one of the tremendous effort we're doing, the whole FinLab is doing, is building the database level annotation. That's the marriage of LC Beanbase and MassWiki. MassWiki is doing, you can check it out, the link is there, is doing annotation in kind of like Wikipedia style. So when we curate data, we are kind of work in a silo and diluted our knowledge into different studies, or one can disagree with another one because there's certain judgment call in that. So in a database level, centralized location, we get to build on each other's work, or debate on current annotations, or refresh the accumulated knowledge from different studies, from different expertise. So this was running exposome cohort, actually, from previous the same run on Astro, and we see those exposome compound drugs, and even the derivatized format for that. In this case, is glucuronide and a form of a drug. So in conclusion, I shared with you, we tested and investigated Excidian Orbitrap to make use of their extended dynamic range, which we get to see really traceable amount of low abundant metabolized exposome compound, meanwhile still not sacrificing the detection of high abundant compound. The squad mode helps a lot to gain the sensitivity, even 100 times more sensitive than MS1-based quantification. There are solutions for informatics like MassCube. We want to do it fast in one click, and they have different peak detection algorithm. And our database level annotation and data processing, which is LC Beanbase and MassWiki. If you want to hear more about it, Oliver will talk about MassWiki as a poster today. And also we have Yinjui talk about nanoflow that enhance the number of annotation for flavonoids a lot today. I would like to thank the PI, our PI, and our team in the FinLab. Everyone has their niche of expertise, and together the force is strong. And I'd like to special thanks for Uri. Uri and I both have the sparkles when we see, oh, new technologies, but we have come from different backgrounds, and it's very fun to bounce ideas with each other. I'd like to thank our collaborator, Rima, who gave us the cohort and dive into the exposome, and our collaboration with Thermo Fisher, Susan's team, Susan, Bashar, and Rahul. That's very fun to work with. And it is the constant innovation that Thermo Scientific provides that keep continuing driving the discovery in metabolomics. With that, I would like to thank everybody and give me more input. Thank you.
Thank you all for such a wonderful opportunity for me to talk about some of my research. Today I'll be talking about the comparative assessment of various squad workflows for the analysis of organic acids, comparing multiple chromatography techniques. So it's always really exciting to come to ASMS and see all the diverse approaches everyone has to kind of study the same thing in terms of metabolomics. What are the kind of the chemical mechanisms that make life possible, right? And so if you've ever been involved in the method development or just a method selection phase of your research process, you're going to find that every decision you make in that process is going to come with some sort of compromise, especially when you're considering what type of separation technique am I using, what type of chromatography. And so to try to understand a little bit more about what those compromises might be, and to also kind of work towards the goal of having a more comprehensive chemical characterization of like the total metabolome, we've been starting to stockpile a bunch of pure organic standards, which includes collections of fecal metabolites, pesticides, VOCs, pharmaceuticals, our organic acids that I'll be focusing on today, as well as some complete metabolite libraries that we're working with. And we're going to be working with organic acids because I personally find them very fascinating. It's hard to think of a lot of metabolomic pathways that don't directly involve organic acids, or at least indirectly are very intimate with organic acids. So if you're curious about any processes involved with like energy production, amino acid metabolism, bile acids and steroids, immune regulation, or like xenobiotic metabolism, you're going to need to be able to have good methods to look at these organic acids. And so luckily we have a good stockpile of organic acid standards consisting of 390 unique organic acids that have at least a few examples in all these examples, or in all these pathways that I've mentioned, with plenty more. And so overall, we're hoping that we can use some optimized chromatography approaches with some novel squad workflows to get a more comprehensive picture to look at organic acids in a little bit more detail. So why are we going with squad when we have such a large kind of panel of organic acids? If we have enough coverage, then maybe just a PRM is enough. But with squad, I think we want to move towards that direction. If you're going to set up a PRM or a targeted method anyways, there's literally no additional investment that you need to make to operate a squad method compared to like a traditional targeted analysis. You just have to kind of change how you operate the instrument and acquire that data. And so in an ideal world, we would be able to kind of have all the standards we want for all the targets we would desire to quantify, but realistically, it's costly, it's kind of a pain to maintain and to operate these large-scale quantitative methods, or you might not have the standards available, or might not know what to look for yet, right? And so by implementing a squad technique, if you have a squad-capable instrument, you can just kind of utilize acquire X and then inject the samples in such a way that you can harness the power of both like robust quantitation while never keeping the door, while keeping the door to discovery open and being able to make untargeted analyses possible. So with that panel of 390 organic acids, we just grouped them into non-isomeric isobaric solutions, and then we ran it through a handful of our LC-MS platforms. So we have a Vanquish HPLC, and we first compared some reverse phase separation techniques. We had C18 and C30, and we created a squad technique for both the positive mode analysis and the negative mode analysis for both C18 and C30. We then wanted to kind of look at the more polar metabolites, and so we've seen a lot of people utilize Hillock. So we decided to use a BEH amide Hillock separation technique and created a positive and negative mode separation technique there as well. Next is one that I personally find very exciting, which is ion chromatography. Ion chromatography is great. A lot of people use it to look at small anions and cations, but it works really well for metabolites as well. One of the things I really love about it is you only need to feed it water. You don't need to buy these organic solvents. And once you get it going, it operates just like an HPLC, but just a little greener, maybe a little cheaper to keep running. Next is one that is a little bit different, which is the GC. And since we're working with a lot of these small polar metabolites that don't like to go into the gas phase super easily, we conducted a derivatization for them with, by trimethylsilation, separated them with an RTX-5MS column, and then we're able to analyze them with the Exploris 480 using electron impact ionization. And so to develop the squad methods for the LC configurations, we started by needing to make our mass list so we can start to organize our fragmentation spectra. So we just ran the standards, gathered the necessary information, mass to charge, retention time, and then we could feed that into Compound Discover. We can start to organize and collect the different MS2 that we would need for later downstream analysis, right? And so one thing that we noticed is there's a handful of overlapping organic acids where you'd see it in one method and the other. And so we wanted to avoid redundancy and creating too many like repeat, too many repeating collections of these MS2. So we decided to select the highest purity MS2 just as like a measure of any co-isolated ions dirtying up that fragmentation spectra. And so once we had the purity selected fragmentation spectra, we could load that into MZ Vault. We could use it for untargeted analysis in the future if we go that route. But in this case, we then use that to build our compound databases and TraceFinder so we could start building our parallel reaction monitoring methods. And so we conducted our PRMs using the linear ion trap, since we're using the Orbitrap Fusion Tribrid for its sensitivity, but also so we can constantly use the Orbitrap for the discovery portion of the squad method. We had a single target ion that we used for calibration, and then a handful of confirming ions that we used to just maximize the confidence in whatever we're quantifying or identifying in our case. And so when we started looking at all of the results and for the LC and seeing what organic acids can we look at in each different chromatography approach, one of the things I noticed right off the bat is that C18 and C30 had a really high amount of these compounds that we were able to detect, which is not necessarily what I expected if I'm looking at these polar charged metabolites, right? But as I was going through that purity kind of filter and also recording all these retention times, one of the things that I noticed is that these reverse phase separations, although I can detect it, oftentimes I'm not getting great separation or great retention on these columns, and we're also getting kind of lower purity scores. And this is kind of represented here in this example to the right. I have an XIC from one of the groups that I ran, so I have 10 standards that I ran in C18 negative mode, and then I have the same 10 standards ran in IC. And in C18, I had 9 of these compounds detected with grade MS2, and then in the IC, I had 7 of these detected. But if you notice kind of the spread in the retention times there, I started raising a few questions as to how clean are these spectra going to be, how reliable can I quantify these in real samples once I have a dirty matrix. And so we decided we wanted to make an extra distinction here. Distinction between detectable and something we can identify, along with something that we can quantify with confidence. And so we removed all the compounds that came out really, really early in the run. So we associate with the dead volume or just things that weren't retained well. And once we kind of separated out the detectable and the quantifiable compounds, we saw a very different distribution in terms of how the compounds we can see with the different chromatography approaches. So right off the bat, we saw that ion chromatography had some great performance. We had 133 compounds we could reliably quantify with ion chromatography, and we had 0 of them that were excluded because they're all retained really well through the ion exchange mechanism. When we looked at the HPLC-based methods, whether it be C18, C30, or HILIC, we saw that they all had a very similar number of the total quantifiable compounds. So then that raised us questions about what are the sensitivity of those 100 or so compounds, and are those the same 100 compounds between those different chromatographic approaches? And so just very briefly, I had some LOQs plotted here that we can look at the median values. So we don't see the specific compounds here, but we can see that across the board they're pretty similar. They're all within like an order of magnitude of each other. The only thing that really stuck out is the fact that the HILIC mode maybe had a little bit more of a spread to it and a slightly higher median LOQ value, but that likely had to do with kind of limitations in the injection volume to maintain nice pretty peaks in HILIC. But the real question that I was stuck on was kind of what fraction of the organic acids am I looking at with each of these techniques? And so we combined all the results for positive and negative mode between these different chromatographic separation techniques, and then plotted them against the superclass using the classifier ontology, and saw some really interesting patterns here. We saw that ion chromatography performed really well with these small organic acids and their derivatives. We saw that they performed really well with these benzoic acids, and then these lipids and lipid-like molecules, although they were leaning towards the smaller side of this superclass of molecules. In the reverse phase negative mode, whether it be C18 or C30, we saw them perform well with these lipids and lipid-like molecules. We saw them perform well with these benzoic acids, and maybe not quite as well with these small organic acids and these more polar compounds as we might expect going into this. For positive mode, we saw that HILIC did really well looking at some of these organic acid derivatives, but one of the things that we really wanted to point out is that it did really well with these nitrogenous compounds. So we had a handful of nitrogenous compounds that we could only see in positive mode, as well as these organic heterocyclic compounds. And when we started to piece or pick apart the individual differences, we saw that these HILIC separations did really well with compounds that have these active amine groups in them that IC really struggled with. And so one of the things that I wanted to walk away with is if I'm limited on time and resources, and I wanted to come up with maybe a 2-injection way to compromise or to study the organic acids as best as possible, what are going to be like the most complementary combinations there, right? And we saw that the HILIC positive mode and the IC negative mode gave us the most quantifiable compounds when we combine those techniques. So we had a total of 259 organic acids that we could quantify in total between all of them. But when we just look at HILIC positive and IC negative, we're able to get at 230 of them, which is a good proportion of the total that we could look at in this study. I would say the second best approach is going to be this reverse phase, where C30 positive mode slightly outperformed with our panel of organic acids than C18, but we're still using that IC in negative mode here. And there was some slight overlap in terms of the compounds that we could see in IC and reverse phase separation, but still it was pretty minimal that we're getting a nice widespread in the organic acids we can look at here. Overall, I would say if you have to make the decision, you would want to tailor that to the application you're looking at. So if you want to look at these amino acids, these polyamines, and nucleotide synthesis, leaning towards that helic positive with IC negative is going to be a great option for you. If you were curious more about bile acids and fatty acid metabolism while maintaining the ability to look at the central metabolism with IC, then that C30 positive and IC negative would be a great combination for you. So the GC analysis was definitely a little bit different than the LC, just because we had a very different kind of workflow up to it and different type of instrumentation. So to make the squad methods for GC, we started by looking at the structures of each of the organic acid standards, and then just kind of the desired reaction product, the derivatized versions of those molecules. Once we had an idea for what all of the derivatized molecules should look like, we did a search through some existing GCMS libraries that are well curated, but we found that a lot of them are in low resolution fragmentation only. And so despite the fact that we were able to find most of the compounds, the TMS versions of these compounds in those libraries, it made some of the assignment a little bit difficult, and also kind of left me wanting a little bit more. For using a high resolution instrument, it kind of sucks to be stuck matching to low resolution spectra. So to combat this, we looked at the structures of the various TMS molecules and then calculated what those fragments should be to then kind of come up with a calculated fragmentation spectra for those. We had a handful of compounds that weren't represented in any of these spectra, whether it be low or high resolution. So then we went with an in silico fragmentation approach to predict those fragments. We combined those to then build a spectral library and then went through to make a complete and true spectral library and started testing the GC performance. And so this was a little bit more time intensive than we initially thought it would be. We dealt with some cool challenges along the way, but we were able to get through at least 150 of the organic acids so far. And one of the things that we saw was a really high detection rate. We were able to get through a little bit over 70% of the organic acids detected this way, whereas in the LC approaches we had 65%. So saw a little bit better performance there, but we also saw a lot of these compounds that we weren't seeing in the LC modes present in the GC approaches. And so what was really exciting to me was those organic acids I couldn't see in LC and IC. Maybe it has something to do with the fragmentation or in the ionization there. But we saw a great quantifiable range, giving us a lot of hope in terms of what GC is capable of in the future, especially when we start developing these workflows a little bit further. And then the last thing I really want to touch on is I've been talking about the quantitation part of Squad the whole time. I think that's one of the beautiful things of Squad is you can just focus on the quantitation, that the discovery data is always there for you. So we had some ongoing work in the lab where we have a marine model organism, the Japanese Badaka fish. We exposed some to this benzo A pyrene, and then we had a control group, and we wanted to see if Squad could really look at the metabolomic differences between those groups. When we looked at the quantifiable differences, we saw that we had 50 quantifiable organic acids between them when just looking at the IC Squad method alone. A handful of those were different, a handful of those were the same. But when we ran that same data through our usual untargeted data analysis pipelines, we had a high number of tentative structural identifications matching it to spectral libraries like MZCloud or ChemSpider, and then around 700 molecular formula that we were able to calculate for them as well. So overall, we saw that we can really capture these differences in the metabolome with Squad methods, both in the quantified portion and the untargeted portion, giving us a lot of hope to utilize these methods in the future. So overall, we were able to come up with a spectral library with around 260 organic acids with high MS2 purity. We saw that helic positive and IC negative was a great combination, and C30 positive and IC negative was also a great combination depending on the application you're going for. We saw that the GC provides a lot of potential, especially upon further development, so we're really excited to see that through. And then finally, the IC is something that I think is really exciting. I think maybe could capture some of your guys' attention, and hopefully we can see a little bit more representation of the IC in the metabolomics world. And we saw that squad is an absolute great approach to kind of solving your metabolomic research questions. So I just want to thank my lab group, my dissertation advisor, Dr. Hussein Abdullah, for helping me on the data analysis and supporting me throughout the entire way. And then also the Thermo team for all the laboratory support and method development. I couldn't have done it without you guys. I have a poster today, so feel free to stop by for some individual questions and to chat it up. But thank you guys very much.
Hi, good morning, everybody. Like I said, my name is Olivia Murtaugh. I'm a graduate student in the SUE Lab at the University of Texas at Austin. And I'm really excited and really grateful for the opportunity to share my work on using microflow chromatography to balance sensitivity and throughput of targeted lipidomics. So just to kind of touch briefly, there's several different parameters that will affect sensitivity and throughput of various methods, but today I'm going to be particularly looking at the flow rate and the acquisition mode of targeted lipidomics and how that can affect both of these parameters. So our LC flow, typically with lipidomics, is an analytical flow, so somewhere between 200 and 800 microliters a minute, right? And they're very high throughput. These methods can typically take a shorter amount of time, and they're very robust. However, they do suffer from sensitivity issues, right? Ionization efficiency can be lacking, increased ion suppression, and additionally, in order to maintain that sensitivity, you typically have to inject a larger amount of your sample. And as we move down the scale, we get more and more sensitivity, right, which makes sense, but they also can suffer from some other issues in terms of nanoflow. There's different robustness issues, there's different reproducibility issues. And really with capillary and microflow, there's still some territory there really to be explored still. Next, thinking about our acquisition mode. So with lipidomics, we typically think about two primary methods, our untargeted and targeted, right? So your untargeted is going to be your high resolution detectors and your data independent or data dependent acquisition. Several different pros and cons of all of these, right? Less method optimization with this, but also you get that global profiling and that discovery. But that comes at a cost of slower scan speeds and potentially that less sensitivity. And again, that increase in your data complexity, right? You're trying to match back these spectra to identify a specific lipid or identify a specific metabolite. And then with targeted, again, it's quantitation mostly based, right? So you can actually quantify your lipid of interest faster. It can be potentially more sensitive depending on your setup. But there is that lower mass accuracy with a detector. You have to optimize your methods, and you're limited to that list that you're inputting into the instrument. So what we're trying to do is combine several of these things into one method. So we're using microflow, again, to kind of increase that sensitivity while keeping the throughput and the discovery, as much as we can, but increasing that sensitivity and that targeted quantitation with SRM or MRMs. So our instrument setup is we're using a triple quad, so the TSQ Quantus Plus. And using heated electrospray ionization with a high flow needle insert, right? We're going to be using something that's greater than that 5 microliter a minute range. And again, just doing selected reaction monitoring or SRM acquisition. And then we're using the NEO, so we have the setup in the direct injection mode, so no trap and elute. And again, we've converted these fluidics into the micro inner diameter, so the 50 micron inner diameter compared to the 20 micron on with the nano. Our mobile phases are some pretty typical lipid mobile phases, so we have the addition of ammonium formate for ionization of those neutral species. And an increase in IPA in order to actually elute some of these very hydrophobic lipids. So the really interesting part here comes with the type of column we're going to use, right? We still wanted to do reverse phase, but we needed a different column. We needed something that actually fit our specifications. So we used a microbore column. And there's several different things I was thinking about, specifications I was thinking about when I was trying to think about buying a column or picking a column. So what stationary phase are we going to use, the particle size, how much separation do we want, the inner diameter, which is going to kind of dictate your flow rate, and then again the length how long do you want your column, how long do you want your gradient to be, how much separation do you need added. And then again, your pH, your temperature, and your pressure limitations as well. So again, another thing is too with the NEO, the max flow rate is 100 microliters a minute. And so how far do I want to test the system? Do I want to reach the upper limit of the max flow rate, something that's 80, 90, 100 microliters a minute? Or am I going to stay more in that capillary, lower end of the microflow range, anywhere from 10 to 50 microliters a minute instead? So before I get into my specific columns and what I did, I wanted to introduce how I optimize and benchmark my microflow chromatography first. So we used the Splash lipidomics, which is just a pre-mixed internal standard, deuterated internal standards that represent a majority of the lipid classes. And here I'm really going to be focusing our neutral glycerol lipids, so our diacylglycerols, our monoacylglycerols, and then our phospholipids and lysophospholipids. Those are the lipids that we're typically interested in the SU lab. And then we just did a 1 microliter injection of our diluted mix. So the range was anywhere from 2 to 235 picomole. We had a 10-minute method, so starting at about 15% mobile phase B, working up to 99% in the stepped gradient, and our flow rate was 25 microliters a minute. So I chose 2 different stationary phases. So our traditional C18, as I like to think of a traditional C18 that's typically used for a lot of lipidomics work, it provides great separation. And then again, out with a C12 column. So slightly less hydrophobic, a little less separation, but pretty comparable. And then both columns have similar particle sizes, 3 micron versus the 2.6 micron. And then 0.5 millimeter inner diameter. So typical for microflow, anywhere from 0.3 to 1 millimeter. And then a pretty large length, 150 millimeters, 15 centimeters. I wanted something that provided a little extra separation, a little time to actually make my gradient. So in looking at the 2, these are just our total ion chromatograms of our injected lipidomics. As we can see already with the C18, we see some of the peak tailing and some peak broadening, and as well our intensity difference. The C12 has a slightly higher overall intensity. So when we break this down into a couple different standards, we can actually see what I'm talking about with the broadening and the tailing. So this is just LPE 18D7, so lysophospholipid deuterated standard. And with the C12 column, we see a pretty nice peak shape, but with the C18, we can kind of see some peak fronting here, right? Some early elution. And then with our diacylglycerol, so our DAG D7, again, additional peak tailing, and the C12 peak shape is a little bit sharper, a little bit more concise. Same thing with our phosphatidylcholine, our phosphatidyl standard. Okay. The next thing that was really interesting and something that really helped make my decision on what column to use was the back pressure. So the C12 had a back pressure of 280 bar compared to 540 bar with the C18. And so you may say, well, you can just lower your flow rate, right? You can decrease your back pressure. Well, I wanted to keep it at this 25 microliters a minute because I wanted to have a little bit faster of a method as well. I wanted something that would not push the column, but it would be just fast enough that I could have a shorter time. I could actually start my gradient at a little bit higher percent B, and I could just separate these things based on class and based on the fatty acid chain saturation and length without sacrificing sensitivity and sacrificing a lot of time for, elution and washing. So additionally, the other thing to think about is that typically with these 2.6 to 3 micron particles, column particles, the max back pressure there is about 600 bar. So if I'm running this column at 540 bar consistently with every run, I'm really kind of hitting almost that max over and over again. So I wanted something that would decrease that back pressure. So in saying all this, I chose the C12. And I ran some of our typical standards. So these are just standard lipids that were extracted from cell cultures. And I saw that the C12 still provides separation based on the fatty acyl chain length. So we have 14.0, 16, and 18, and we can see that increase in retention time there. And additionally, we see the decrease in retention time as the level of unsaturation or the degree of unsaturation increases as well. So typically, these are some parameters that we help use to identify lipid species over others. So C12 still provides that level of separation there. And again, these peak widths look pretty clean. Some tailing, but Not bad. So next, I wanted to test this method. I wanted to see how sensitive it actually was, and if I could use this for our specific standards and our specific workflow. So I generated the limit of detection and limit of quantification just using lipidomics, just neat diluted lipidomics with several different technical injections. And here's just representative. This is the diacylglycerol D7 standard. And I found that the limit of detection was in the peak of the femtomolar range for the limit of detection and limit of quantification. And this was seen with all of our standards that we were interested in. So in that single to double digit limit of detection, limit of quantification range. So very, very sensitive. Then I wanted to apply this right to actually identifying our endogenous lipid species. So again, I was trying to make our methods as short and as concise as possible, but while profiling as many lipids and as by specific class as possible. So I optimized different gradients for the phospholipids, the lysophospholipids, the DAGs, and the MAGs. So with the MAGs, there's a 4-minute runtime, and I'm measuring all MAG species, so 24 different species. Same thing with the DAGs. It's 6 minutes, a little bit longer, but we're measuring 276 different species. And then with the lysophospholipids and the phospholipids, I wanted to identify those specific lipids at molecular level, right? I wanted to observe both of those fatty acyl chains. And so by following the lipidomics standards initiative, I have both fatty acyl chains as my product ions there. So with the lysophospholipids, again, in negative ion mode, 144 different species, a 4-minute method. And then the phospholipids, again, 276 species and a 6-minute method time. So in order to generate my fragments and generate my transition list, I turned to Lipid Creator. So this is a great program, made my life a lot easier. And just kind of a representative here, you can put in your specific lipid chain and double bond level of unsaturation, and it will give you which fragments to expect or what you can identify. And then from there, it will give you those precursor masses and then your product ion masses, which you can then send directly into Skyline. So I did this for all of the different lipid species that we were interested in. And then I optimize those collision energies, again, using Skyline. So Skyline will give you a generated collision energy value based on the type of instrument that you're using, but it would also create what's called these stepped collision energy like transitions that you can then run and then optimize your collision energy for the best peak area or best intensity. So the original CE was about 25 volts, and that peak area is here. And then with the step -2, so a lesser collision energy, we had a slightly higher peak area, so that was now our optimized collision energy. And so we did this for all of our different species, all of our different transitions, and then we just exported that targeted transition list directly into our method. So now I'm going to get into why are we doing this? What are we doing in the Sioux Lab that makes us want to measure these specific lipids, and why are we interested in them? So we primarily look at the inflammatory signaling pathways, so using those polyunsaturated fatty acid containing lipids that are then metabolized by primarily seen here serine hydrolases into your endocannabinoids, your fatty acids, and then into your lipid mediators like prostaglandins and other eicosanoids. So one example that we like to use is the use of non-steroidal anti-inflammatory drugs, so your NSAIDs like ibuprofen, Advil. When you take them, you're inhibiting that COX-2 pathway, and so you're seeing a decrease in your prostaglandin E2, your PGE2, which means a decrease in the pro-inflammatory signaling pathway, but an increase in your arachidonic acid levels. So what we're doing is we're looking a little upstream. We're looking primarily at this enzyme diacylglycerol lipase, and specifically the beta isoform. So previous studies have shown that whenever you genetically disturb or whenever you pharmacologically inhibit or ligand the active site of Dagl beta, you also see this decrease in pro-inflammatory signaling. But you also see a decrease in your endocannabinoid, your arachidonic acid, and you should see typically an increase in the diacylglycerols. So what we did is we took wild type and DAG lipase beta knockout mice tissues. Specifically, we're looking at some of these peripheral tissues as DAG lipase beta is expressed in the peripheral nervous system and in peripheral tissues. And we just wanted to compare the differences between these two mice at a very broad level, right? What are the changes in all these different lipid species? So we took the kidney, the spleen, the pancreas, and liver. We down homogenized them in order to kind of lyse them up, break them, and then normalize the tissue volume as well. We extracted them some pretty, well-known, obvious techniques of Bly-Dyer with our spiked and internal standards in order to extract those neutral glycerolipids, and then a modified Fulch where we added hydrochloric acid in order to acidify and elute some of those charged lipid species. We dried them under a nitrogen stream and then just resuspended that extract in IPA, isopropyl alcohol, and methanol, and about 100 microliters in order to actually dissolve and all those lipids that were there. And then from here, we injected half a microliter of our sample into our setup, right, our Vanquish Neo coupled to the Qantas, and then used TraceFinder in order to integrate those area under the curve, and also to use the confirming ion portion of it to identify that we actually are measuring that specific molecular lipid species and not just the total group. So we took that peak area, normalized it with our internal standard and the known concentration that was spiked in, normalized it again to the amount of tissue that was actually extracted to get our lipid concentration as femtomole per milligrams of tissue. So what we saw was really interesting. So on the left here are all of our down-regulated lipids. So these are all our lipids, our lysophospholipid phospholipids, DAGs, and MAGs grouped together. And we did the full change of the knockout of the wild type. And what we saw is that in these tissues, we're seeing a downregulation in the unsaturated containing lipids, right? So anything that is less than 2 degrees in saturation, something that is unsaturated, that's saturated or monounsaturated, isn't these black dots, and the other colorful dots are differing levels of saturation. And so we saw this really interesting, like I said, downregulation in pretty much all of our tissues, lesser in the spleen, but in these peripheral tissues. And so then we extracted those out, and we actually found that most of these polyunsaturated fatty acid containing lipids were actually diacylglycerols. So it's a little counterintuitive to what we were expecting, right? As we inhibit DAG lipase beta, we should see an increase in diacylglycerols, especially in polyunsaturated fatty acid containing diacylglycerols, because it's involved in that inflammatory pathway. But we saw a decrease in the knockout and an increase in the wild type. And again, seeing some other increase in the MAGs and phospholipids, but not as drastic as the DAGs, kind of giving us an idea that we're doing some kind of rewiring of metabolism in these knockout mice. So here, in conclusion, we presented microflow LC with SRM methodology as a means to improve our sensitivity and throughput. So again, we have these femtomolar LOD and LOQ, just using our splash lipidomics, compared to typical LOD, LOQ in the nanomolar, picomolar range. We have pretty good sensitivity. And again, I created tailored methods for each of these lipid classes. So we've optimized the transitions, the collision energies, and the gradients. Really short run times between 4 and 6 minutes, and we can identify the specific molecular species. And using this, applying this to our own interest in lab and our own pathways and metabolism that we're studying, we are seeing this interesting increase in the PUFA-containing lipids in our wild type instead of our knockout, which is a little counterintuitive to what we expected. So we have a lot of really interesting data and metabolism pathways to actually go back and study again. With that, I'd like to thank everybody in the Sioux Lab, especially my advisor, Dr. Ken Sioux. We have a great lab, and again, our University of Virginia counterparts as we moved to University of Texas not too long ago, doing really, really awesome work there. With that, thank you. Any questions?